We've learned about injective functions, a function between two sets that has no collisions, and surjective functions, which are functions between two sets where all points in the codomain are covered by the mapping and no points are left uncovered. We're now going to look at what happens when you start combining these two properties. Think back to several videos ago when we were talking about cardinality of sets. We had this example explaining why it was hard to talk about the cardinality of infinite sets because it can be counterintuitive. In that example, I argued that the natural numbers and the even numbers, in one way of thinking about it, have the same number of elements, even though the evens are clearly a subset of the entire natural numbers, because I was able to construct a one-to-one correspondence between the entire set of natural numbers and the set of just the evens. Because every even number pairs up with exactly one natural number, that seems to say that these two sets have the same number of elements, even though we can't put an actual numerical value on the number of elements because they're both infinite. So these one-to-one correspondences are a way to express the fact that two sets have the same cardinality even if computing the number of elements in that set is impossible. Looking at this one-to-one correspondence now, you might notice a few things. First, this is correspondence as a function from the set of natural numbers to the set of even natural numbers. Every natural number has an output, and no natural number gets split off into two different outputs. Not only that, this function is injective. It would take a little more careful argumentation to prove it, but the diagram should convince you that there are no collisions here. And finally, this function is not only injective, it's also surjective, because every point in the codomain, the set of all even natural numbers, does have something mapping to it, namely the natural number that's half of the even number. So this is a function that is both injective and surjective, and that's what makes it a useful counting tool. These kinds of functions are so useful for practical purposes, in fact, that we give them a special name. We call them bijective. A bijective function from A to B, sometimes just called a bijection, in other words, is just a function that is both injective and surjective. The function we just saw from the natural numbers to the even natural numbers, given by f of n equals 2 times n, is bijective. But as always, let's look at some more examples and non-examples. This mapping from the set 1, 2, 3, 4 to the set x, y, z, t is a valid function. Every input has an output, and only one output, not two. And it's surjective because every point in the codomain has something in the domain mapping to it. And it's injective because there are no collisions. As you can see, every pair of distinct or different points in the domain map to distinct or different points in the codomain. Since the function is surjective and injective, it's bijective. Notice that any two sets that are connected by a bijective function have to have the same number of elements, but the converse isn't true. Just because a function goes between two sets with the same number of elements, it doesn't make the function bijective. Here, for example, are two other functions between the sets 1, 2, 3, 4 and x, y, z, t, neither of which are bijections. The first one, g, maps everything in the domain to x. This is a massive collision, so the function is not injective. And since it's not injective, it can't be bijective. The second one, h, is not surjective because nothing maps to the point y. And since it's not surjective, it can't be bijective. You probably see that neither of these two functions is either injective or surjective. Is it possible to have a function that is one but not the other, either injective but not surjective, or surjective but not injective? The answer to that question is definitely yes. A good example is the birthday function we looked at earlier, mapping the set of all students at your university to all the days in the year. Assuming your student body is bigger than 365 students, there are two things that are 100% likely. That for each day of the year, there will be at least one student who was born on that day, which makes the birthday function surjective, but also there will be two students who have the same birthday, which makes the function not injective, and therefore not bijective. On the other hand, some functions can be injective but not surjective, and here's a simple example. Look at the function g from the natural numbers to the integers. That does nothing but send the input to itself. So g of 1 equals 1, g of 2 equals 2, and so forth. This is pretty clearly injective, since two different inputs will always go to two different outputs, because the outputs are just the same as the inputs. But this function is not surjective because there are a lot of elements in the codomain, such as -1, -2, -3, and so forth, that are never hit. So this may look like a one-to-one correspondence, but it's not actually a bijective function. Again, one of the major applications of bijective functions is that they are tools for counting things. Here's an example that will be really important for us later. Look at the set A of all 8-bit strings that have exactly 3 1-bits. For example, 111, 0, 0, 0, 0, 0, and 0, 1, 0, 1, 1, 0, 0, 0 are elements of that set. Now look at the set B of all 8-bit strings that have exactly 5 1-bits, like 0, 0, 0, 1, 1, 1, 1, 1, or 1, 1, 0, 0, 1, 1, 0, 1. It's not obvious how many elements are in each of these sets. We'll be solving that problem later, but I can show you that these two sets have the same number of elements, that is, the same cardinality, without actually counting the number of elements in either one of them. I can do this by setting up a bijective function from one set to the other, and here's how that might work. Let's let f be the function from A, the set of 8-bit strings with 3 1s, to B, the set of 8-bit strings with 5 1s, defined like this. Given an input, which is an 8-bit string, the output is another 8-bit string that I get by just flipping all the bits, 1 to 0 and 0 to 1. For example, 111, 0, 0, 0, 0, 0 would map to 0, 0, 0, 1, 1, 1, 1, 1. Now, this is a valid function because every input does actually have an output, and the output actually does belong to the codomain because if I start with a string with 3 1s, that means I have 5 zeros, and so the output will be a string with 3 zeros and 5 1s. And also, no input string gets split off into 2 outputs. Moreover, not only is this a valid function, it's an injective function, because if I take 2 different inputs, they are different because they have a different bit in at least one place, and that bit will be flipped into different output. And also, this function is surjective, because if I pick a string from the codomain, to find the input that maps to it, I just change all the bits, and this will give me an 8-bit string with 3 1s that will map back to the codomain string that I started with. So this bit flipping function is a bijection between the sets, and that means that there are exactly the same number of 8-bit strings with 3 1s as there are 8-bit strings with 5 1s, even though we still don't know how many those are. In this video, we learned about bijective functions, or bijections, which are functions that are both injective and surjective. And we learned that they are used for showing that 2 sets have the same cardinality even when we don't know how exactly to count the number of elements in those sets. Our next video is the last one in this module, where we'll look at some special functions of use to computer science and see what properties they have.